Welcome to this session. We're going to be diving into electrical troubleshooting. This is 20 minutes of high impact, fast paced electrical troubleshooting. I want to get through to you one or two things out of this 20-minute session. The first thing is, who the hell is Trevor Matthews? I'm a refrigeration technician turned trainer, 20 years in the industry, and have trained thousands and thousands and thousands of technicians all over the world. And now I built a company called Refrigeration Mentor to help techs stop guessing and leveling up. And I like to say, let's get a conversation going. Okay, refrigeration, electrical troubleshooting, how to stop guessing and start proving. This is so important. You got to prove your stuff. The real problem is a lot of electrical failures are misdiagnosed, because one of the things that I've seen a lot over and over again is the proving method. We got to prove that there's something wrong, something has failed. Parts changing is not troubleshooting. Guessing costs time, it costs money, and it costs confidence. The one rule is, if the load is not running, voltage is missing or being blocked. That is the thing. Voltage is missing or it's being blocked. That's why something is not running. Okay, today's goal is to find out where voltage disappears. All of you, I know how to use a meter, but we have to be safe. This is one of the most important things in refrigeration, is we have to be safe. We don't want to get hurt. So we want to talk about where the voltage, you got to know how to use a meter. Someone needs to teach you if you haven't used one before. Two circuits always exist. The two circuits are the power circuit and the control circuit. Okay? Very important to understand the two circuits. Control circuits allow or block power. This is it. They allow power or they block power. You guys understand this, because when we have a series circuit, when something opens or something everything stops. One thing opens, everything stops downstream of it. Downstream means after that switch. Upstream means before that switch. Now, when we have a parallel circuit, loads can run independently. What does that mean? Well, we'll see right on here, we have a crankcase heater and a receiver heater. Okay? If one of those fails, so for example, if the crankcase heater fails, that receiver heater can still work. Okay? So this is a parallel circuit. What a diagram really shows is logic, and that's kind of what I want to teach you today, logic. It's not where those wires go. It doesn't matter where the wires go. It matters if you understand the logic behind it. This is so important. How does that voltage move? Okay? We want to read diagrams from left to right. From left to right. So as we can see here, we start and our main power comes down from our L1, L2, L3. When we're looking at a diagram, we're looking at a control circuit. We have L1 on the left, we have N or common or L2 on the right. So you got to remember how to read these diagrams. It is so important. Every electrical problem fits in one bucket. No power, block power, or failed load. That's it. No power, block power, or failed load. When we understand this, this is going to really help fast track your troubleshooting. Stop measuring to ground. Stop measuring the ground. This is here what tricked me up for years, what took me a lot longer to be a really good technician and really troubleshoot a lot quicker. What do we use ground for? We use ground to check for potential. That's safety. You shut off a breaker and you're going to put your hands on the wire. You want to make sure there's no power there so you don't get a shock. When you go to ground, it lies. It lies. And we'll talk about that and why does that lie. And then when we get into 208, 230 volts, we really need to understand the difference than when we're going through like a 120 voltage circuit. Okay, or 24. Most powerful measurement. Measure across components. Measure across the components. Now, this is where you start to understand. I used to jump and hopscotch all over the place. There is going to be something on steps that I'm going to talk about, a strategy for you. Every time you're electrically troubleshoot, it doesn't matter if there's 1,000 points or if there's 10 points. You have to have a strategy every time. And when you understand that strategy, you're going to learn faster, you're going to troubleshoot quicker. A good closed contact, what does that really mean? So if we have power to a circuit and we have a switch and we go across that switch, what do we get? We get 0 volts. Okay? If that switch now is open, what do we get? We get potential. This is what it's called, potential. We get whatever that circuit voltage is, 120 volts in this example. So if it's closed, you get 0. If it's open, it's 120. We are testing that switch. When we get into the next step is line to load tells the truth. Why do we do this? Especially in contactors. This is so, so important in maintenance. And you can really find out if contactors are bad or good with your meter, as well as a thermal imaging gun is very, very good. But with your meter, you go across it, and you should get zero potential because it's closed. If you get 6 volts, 10 volts, there's a voltage drop, and that is probably some sort of pitting, some sort of dirt in those contactors. You really want to step that up and make sure. Where did the voltage stop? This is so, so important. I have a coil pulled in, but the load is dead. So for example, down here, you can't really see it right now, but condenser fan is red down there. My coil's pulled in, but my fan is not working. Now we got to go to the root of the problem and check why is that condenser fan not working. Our safety string, one open hides in plain sight. So in supermarket application, or even in an application like this, if you have something that trips off, we usually get a call as something called like compressor proof failure or safety line alarm. Okay, when we get out there, it's how do we troubleshoot this? It hides in plain sight because now we got multiple circuits. We got low pressure control, maybe a high pressure control. We got an oil safety control. We have a over temperature control, maybe a discharge line temperature control, maybe a low ambient control in it. So divide and conquer. How do we do that? Well, we use our meter effectively. We go from this example on this control circuit, we go from common to the middle. Use your terminal blocks. You do not have to be pulling everything off. All the manufacturers today, they have terminal blocks on it. It's a lot easier to troubleshoot today than older systems. And I understand there's a lot of systems that have all black wires and nothing is labeled and they've been butchered over the years. Totally understand. But the newer systems are really quick to troubleshoot. Divide and conquer. So if I went from this point here to my common or my end, I'm in the middle. If I have no voltage there, what does that mean? That means something before it, something upstream is open. Now, if I do have voltage there, that means something downstream is open after it. Does that make sense? So now we really want to understand how to use that meter, and we can break our troubleshooting up a lot quicker. Why techs miss this? Here's a really good one. They check present, not lost. So here's a really good example that tripped me up multiple times in the field. I went up to a coil on a contactor, and I'm like, the contactor should be pulled in. I got 24 volts. This is an example. I got 120 volts before the coil to ground. I got 120 volts after to ground. Well, what does that really mean? I go across, I got 0 volts. I'm like, oh man, this should be pulled in. I'm getting voltage to it, but it's not pulled in. What does that mean? Well, that means something downstream of it is open. Your neutral is broke, it's loose, or you have a switch in there, kind of like a low ambient control in this example, that is open, that is stopping the path because loads they use the power, they need voltage, they take up power. And if we don't have it finishing in your neutral, your common, your L2 for an example, then that's when it doesn't work. So this is one of the reasons why ground can lie. Condensing unit. This is a condensing unit on it. It looks complex, but you got one simple rule you got to follow. You know, it does look, and you can get different ones that are very messy. But if you follow a simple rule, ignore everything else except what's tripped. So if it's a control circuit that's tripped, that's what you focus on. You don't have to go across all the power side loads and check all that. You got to focus on that area that has tripped. What could it be? You got to start at the source. Where is the source? Well, I got primary power to my transformer, and then I got my secondary power to my transformer. Do I have voltage there or not? Okay, if I do have voltage there, what's the next step? Then we check that circuit. Okay, this example is our low pressure switch. If we get 120 volts across the switch, what does that mean? It's open. Okay. Next, we go, and the low pressure switch closes on drop. For a high pressure switch, as that pressure rises up, when you hit that certain limit, whatever the set point is, that will open up. So we go across it, we get 120, then that's open. If we get 0, that is closed. This is the way switches work. Oil safety. This is one of the big things in refrigeration if you have oil safety sensors. Differential pressure plus time. What does that mean? That means that, okay, I trip out at 7 to 9 PSID or 0.6 BARD. What does that mean? So I tripped, I look at it, oh, I get my pressure differential, it's too low, but it still hasn't tripped the unit yet. Now there's a time delay, a 90-second or a 120-second delay in your Centronics or your Delta Pi's or your Pens or your Danfoss oil safety controls. The time delay relay tricks up so many people. I've seen it time and time again, taking calls and talking to technicians in our training programs. Like I remember one in our CO2 program where a technician said, hey, I got a phase monitor failure. So they go up and they reset it, the unit, and they go across and they got, like, I got all my phases. I got the proper voltage, but it's still off. The thing was, it was the time delay that failed. And so what do these do? Before they do the trip, you set them up. It could be 2 seconds, 10 seconds, 2 minutes on the time delay before it makes that action happen. Contactor coil is the gatekeeper. And really, what we want to know is that, do we have power to that coil, and is it actually doing the action that we want? By pulling in the contactor contacts to make the circuit, okay? If that is not happening, we got to prove it. We got to take our meter out. Do we have voltage there or don't we have voltage? In this example, it says 0 volts. We don't have voltage to that coil, so that's not going to pull in. So what could be the problem? We go upstream. If we take a look at this example, we have a tripped core sense. Okay, this is the oil pressure control. This is just an example, but we got to go upstream before it if we don't have any power there. Okay, it's so important to prove it. Load side matters. So line power doesn't equal operation. Just because I got line power, I have my 575, I got my 208, 230, my 600 volts, my 460 volts on the line side, it doesn't mean that we got load power at this time. Meter placement is so important. We need to visualize. The more you read these, this is how you're going to get better. Like in my supermarket program, one of the main things we're doing is we're reading electrical wiring diagrams, we're getting the diagrams, and we're walking through them step by step. Because if you're not doing this every day, you're not going to get better very quickly. But if you're doing this every day, you're going to be able to troubleshoot systems that you have not troubleshot before, because it takes consistency, it takes practice, and getting your meter out there, you should be able to visualize this. When someone says the contactor's not put in, you should be able to think, well, the coil must not have power. Right? That's one of the things you would think of. You got to visualize this stuff. A real scenario, everything looks normal. I check my meter, I got power on my load side right now. But all of a sudden, voltage, all of a sudden it trips out after 120 seconds. But it was working there a few minutes ago. You checked it, oh, it's running right now. But all of a sudden you have a time delay or you have an oil failure like this, it trips and tells the truth. We got to find that is our job. It's so important. Auxiliary contacts, another thing that is misunderstood. One of the things that's really important is to understand how the switches work. Every wiring diagram that you see is in the de-energized position. In the de-energized position. So this here is closed. So when nothing is on, those are closed. This example here, your crankcase heater and your receiver heater would be running. When it's powered up, all of a sudden, those wouldn't be working. They would be opened up. Then when we get to fan cycling control, there's pressure logic. Well, what does pressure logic mean? So as the pressure goes into some sort of component, a low pressure control, high pressure control, a fan cycling control, it will change the contacts depending on that setting. For this example here, that condenser 2 fan is not running, and you can't see it. In the documents at the end, you can get these presentations for free and just look at them. But the condenser fan's not working right now. We got power to the coil, but it's not working because there's a fan cycling control there. Now, if all of a sudden your pressures get really high and that fan is still not running, then we would have to go and check, see if that pressure switch is working or not. And that's how we would use our meter. Defrost circuits, there is multiple paths. It follows the same rules. If we're working on an evaporator, or a condenser, everything follows the same rules. If you're working on residential, if you're working on light commercial, if you're working on refrigeration, supermarket, CO2, or an industrial, follow these processes. Factory versus field wiring. I've seen this multiple times in training programs. I do startups, I go to startups a lot of the time. And I've seen many times people send me pictures and say, hey, Trevor, system's not working. And then some of the main sensors that need to be wired up are not even wired up because the contractor or the technician didn't take a look at the different lines that need to be wired up or not wired up. Condensing unit manufacturers are great for finding this out. Right here, the straight line wire comes from the factory. Optional wiring if you have something like a low ambient control or a specific control on that. And then field wiring by others. That is us. We need to set that up. Don't ever jump out safeties. Safeties are there for a reason, okay? If you need to do a certain test, like jump a low pressure control to see, to test discharge valves to see if they're working. Yes, you would do something like that. And these are just for tests. You pull it off afterward. You never leave safeties jump because you could hurt yourself, you could hurt the equipment, or even worse, hurt somebody, yourself or another technician. That is normally open confusion, okay? What does that really mean? Normal means unpowered. This, like I said earlier, this diagram, and every diagram you look at is de-energized, okay? That means unpowered when you first look at it. Controls are usually innocent. Prove before replacing. So many parts. Right now, out there in the field, somebody's changing parts that they're not proving. They're like, okay, let's pull it out and just try it. Does it work? No. Okay, let's try another one. Let's put the motor in and change it. Just prove it. Your meter is not going to lie to you if you use it properly. The steps on using it. Follow the path. Okay, smart readings beat more readings. There is only so many tests in electrical circuit. It doesn't matter what unit you're on. I don't care what you say. It could be a big industrial system or it could be a little small. There's only so many tests. It could be like this one here. You got 22. There's only 22 checks that you can do. And a big system could be 10,000 checks, but there's only so many. And if you know all of those checks that you need to do, that's going to speed up your troubleshooting time. It's understanding that logic before. And I'm going to talk about a 6-step process, a repeatable method, okay? Identify the load. What is their load in that? When you're looking at that wiring diagram, count right on it. This is what I do with all my students in my training program. I give them a wiring diagram. I'm like, circle all the loads on there. So if you know every one that's a load, on this example here, there's 9 loads in this condensing unit. Okay? Then you do the same thing for switches. And then you got to find where the power is. So where's the power source? Do I got my coil voltage or not? Or my transformer voltage? This example on this control circuit is 120 volts. Okay, next step, measure the components across the components. This here is a fuse. If I measure across the fuse and I get 0 volts, that fuse is good. If I measure across and I get 120 volts, that means it's open. Okay, follow the path. Now, instead of me pulling off the covers of the low pressure switch or the high pressure switch or anything, I go across it. Do I got voltage? I got voltage across it. Great. What's the next step? Well, then we check across that specific load that we're working on because the crankcase heater is not coming on because we see it was flooded started when it's starting up. So we go check it. Okay, we got voltage across it. How come that crankcase heater is still not working? Then what we do is we prove the failure. How do we do it? We take the power off and then we ohm out that heater element. And if that is OL, is open, that is your problem there. This is how we need to do it. We need to start at the process. Where's the power coming from? What is what we're looking at? And then we got to get to the point where we're proving that it's failure, not just replacing parts. Okay? Final thought, electricity does what the circuit allows, okay? It does what it allows, and this is why reading the diagrams is so, so important. The more, I promise you, the more you read and you use your meter at the same time and you follow it and you write down it, you're going to be so surprised how quickly you're going to learn electrical. Slow down, prove it, and stop guessing. That is really the biggest thing I can tell you because a lot of technicians, even me, when something's wrong and the fire's on there and the customer's telling you and your boss is calling you, it's a stressful situation sometimes, especially when you get hundreds of thousands of dollars of product on the line. One of the things is take your time, take a breath, like anything, and take a look at it, and then just make sure you're using your meter properly, okay? If you're jumping all over the place, hopscotching, you're going to confuse yourself. Get the wiring diagrams. Understand the circuits. Understand where you're putting them and why you're putting them there. Think about it. Take a few minutes. If you haven't done that before, why am I actually putting my meter right here? So, so important. Get this presentation. I know this was really quick and this was fast-tracked, but if you go to refrigerationmentor.com/ETS right now, you can download it just download it right onto your phone. It's the PDF right there. One of the biggest things that I've trained a lot of people on electrical, and I've been trained by some of the best around the world on electrical, and I'm just in refrigeration, and I'm continuing to learn more, is that you got to understand what you're trying to troubleshoot. that logic behind it. We want to understand what is the whole purpose of what we're doing in refrigeration, okay? The whole purpose is that we need to pull in that contactor so that compressor starts up so we can get flow of refrigerant to pull the heat out of the product and reject it to the atmosphere, the heat. So if you want to get another full electrical troubleshooting training, we have one here. You can scan it with your phone, and that's it. Fast track, high impact electrical troubleshooting. Hopefully you enjoy, and I'll take hopefully a few questions because I don't. Where are we at? Smash that one out in perfect time. 20 minutes on the dot. Practice really well. Any questions? Yeah? Intermittent failures. What do you do for intermittent failures?
Basically repeat the process until I can get it to fail.
Yeah. One of the biggest things I used to do, which is a mistake for me, I used to reset. When a system tripped, I used to reset the system. Don't do that. Get your meter out and try to find out where it is for you. If it's an intermittent failure, those can be hard. Because it could be a wire that the only time it trips, you open at a door and there's a short, and the only time it happens is when you open the door. Okay? So, and sometimes it does take longer. Sometimes you have to change a certain part to check that.